Okay, a couple announcements before we get started. Your Module 1 exam will open in zip grade at 2:15. You have 24 hours to do it. Closes tomorrow at 2:15. You have to navigate to zip grade to do that. The exam's not going to show up on your Canvas calendar, so please do not send me an email at 12:16 or 2:16 tomorrow saying that you didn't see it in Canvas. The exam dates are listed on the front page of Canvas where I put the scores. So all the dates are listed there. Don't forget to submit it when you're done. I'll grade it tomorrow after it closes. You can see your scores in ZipGrade. And any questions on that? There's 30 required questions and 6 bonus questions. So today we're wrapping up the chemistry of aromatic compounds. So we're going to look at, again, how these functional groups, when they're on the ring, how do they dictate reactivity? How do you differentiate isomers? And then ultimately, given the substitution patterns, how do you think about introducing the substituents so you get the correct pattern? So we'll start off with some questions that's going to build up to applying this logic. And it says, which of the following correctly categorizes the nature of the substituent on the aromatic ring? So you probably are wondering what these names are. So a lot of these names, again, are just common. They're not IUPAC. So I'll draw the structures below. So acetophenone is a ketone. Ethyl benzoate is an ester. Ethyl benzene is just an alkyl side chain. And then 1-phenylethanol is another alkyl side chain, but now the benzylic carbon's at a different oxidation state. So EDG is electron donating, EWG is electron withdrawing. So they all have the ring in common, and you're asked to determine how does the substituent affect the reactivity of the ring. So if we start with acetophenone, how does the carbonyl group affect the ring? So it's withdrawing, so we can eliminate A and D. So from the ketone to the ester, we're going up in oxidation state, changing the functional group. But the similar thing is the carbonyl, right? So if the carbonyl is electron withdrawing in the ketone, it has to be withdrawing in the ester. And so that would eliminate C. And then for the ethyl benzene and 1-phenylethanol, since they're both alkyl groups, they're donating through induction. The difference, again, is a change in oxidation state. So we would end up with B is the correct answer. So to redraw these real quick and to review again that concept of oxidation state. And it's specifically asking you about the benzylic carbon. And so for oxidation state, we're just counting from the carbon to the number of heteroatoms. So for acetophenone, that would be 2. So that would eliminate A and B. For the ethyl benzoate, that's going to be 3. We have a sigma bond, a pi bond, and then a sigma bond to another oxygen. So from that, we can eliminate C. Ethyl benzene has no heteroatoms, so that's 0. And then 1-phenylethanol is sigma bonded to the hydroxyl group, so that's 1. So we would end up with D. And again, the oxidation state concept is important for us moving forward, because as we start zooming in on these different modules which are arranged according to functional groups, we want to look at how is the oxidation state changing from starting material to product, and then how can we use those manipulations to our advantage. So let's consider this reaction. It says acetophenone going to ethyl benzene. So in that reaction, is it an oxidation or reduction? And then how do those states change? So we said acetophenone was oxidation state 2. Ethyl benzene was 0. If the number goes down, it has to be a reduction. So the correct answer is A. It's going from 2 to 0. And I want to further point out as a preview to the coming modules, since the difference between those numbers, so 2 to 0, in a sense we're skipping 1, right? So we can classify that as a 2-stage reduction. And the reaction that we learned was that Clemenson reduction. It's taking it from 2 all the way to 0. It's not 2 to 1 and then 0. So it's sort of two things to remember. If the number goes down, it's a reduction. If it goes up, it's an oxidation. So that's one way of thinking about it. Another way of thinking about it is, are you increasing the hydrogen count to the carbon, or are you increasing oxygen count? So there's ways you can analyze this and think about it. So toluene, so that's methylbenzene going to benzoic acid. The carbon is starting at oxidation state 0, and it's ending up at 3. So since it's increasing, it's an oxidation. So we're going 0 to 3. And as we learn more and more reactions throughout the semester, again, as you prepare for the final, what classification system you use in terms of knowing these things is the sodium dichromate is the reagent that's going to take it from oxidation state 3 or oxidation state 0 to 3 in one reaction. So it's not going sort of stepwise. Your final product is jumping from 0 to 3 all at once. So the other thing that's important to mention with this example is a preview to where we'll get in about 20, 25 minutes. The alkyl group, the methyl group, so that was an ortho-para director. And now when you change that oxidation state and functional group, it's now becoming a meta director. And so now we have some strategies to control positions on that ring based on what the substituent is. So benzoic acid going to benzonitrile. What type of transformation do you think that is in terms of the class and then oxidation state change? So it's neutral, the number's staying the same. So it's going from 3 and it's remaining at 3. So since these are both electron withdrawing groups, the directing ability is not changing. So that was a little bit about the influence of the oxidation state, how you think about it going up or down. And now let's consider, we've taken benzene, we've put a substituent on it to make it monosubstituted. Now we're going to take that and we want to put a second substituent on it. And the question says, how many possible isomers are there for di-substituted aromatics? So you have 2 substituents, you want to stick them onto the benzene ring. What are the possibilities? So 3. I'm just going to call the substituents A and B. So that's called the ortho or the 1-2 relationship. This is meta or 1-3. And this is para. So para is 1-4. Yep. So from that last slide, in the benzoic acid, you have 3 bonds to oxygen. And then in the nitrile, you have 3 bonds to nitrogen. So because the number itself, 3, is not changing, it's a neutral transformation. So these are the 3 possible scenarios when you have a di-substituted benzene ring. And eventually where we're going with this is how does the first substituent control where you put the second? Once you have a di-substituted, where's the third one going to go? And that gets complicated because you have to look at what are the directing group abilities of each of these. So which one's going to overpower the other one? So if you have like an ortho-para director and a meta director, then it can get you sort of anywhere on this ring, but where do you predict it will go? And so that's where that benchmark where you have benzene in the middle in the strength of the electron donating or withdrawing groups lies. So let's put this to practice in terms of how would we differentiate a di-substituted aromatic that had 2 of the same substituents. So dimethylbenzene. So this has a weird name, it's called xylene. So there's your ortho, your meta, and your para. And it's specifically asking about carbon uniqueness. So which would have the least number of signals in the carbon NMR? So para, how many would it have? 3? Does everyone buy that? So now keep in mind, both of those substituents are the same. So probably the easiest symmetry element to see is you're just cutting it in half, and the top reflects on the bottom. And then the next one, you're actually cutting through those methyl groups. So it has 2 planes of symmetry there. So I'll put some green dots. Those would be the 3 unique carbons. What about meta? How many signals would that have? What'd you say? 5. So that plane of symmetry would be here. And ortho, you'd have a plane of symmetry there, so that would get you, what, 1, 2, 3, 4? So the way that translates is if you're given, I know what you're going to ask.
I told her not to.
Throw that in there as a little humor.
Can I please ask?
Sure.
What's up, dog?
Not much, just chilling. Anyway, so if you're given a carbon NMR on an exam, you're counting the number of signals, right? And so that's what you're figuring out, which one of those isomers is it. So the fact that the numbers are different because of those substituents being the same, you can, come to that conclusion. So it does get a little bit more complicated now if the substituents are different. And so we're going to look at bromoaniline. Again, aniline is just a common name. Like if you didn't know what it meant, like what is the substituent for aniline? It's aminobenzene. So, since you're taking your exams at home or wherever, you can just like Google aniline if you don't know what that means. So let's draw these out and sort of do the same exercise. But keep in mind now that because the substituents are different, you're not going to have necessarily the same symmetry elements as when they're the same. So that would be aniline. This would be the orthobromoaniline. The meta is the 1-3 relationship, and then the para is the 1-4. So now phrased slightly different under each isomer, how many C13 signals should each have? So if we start with the 1-2, is there a reasonable symmetry element? So you're starting with 6 carbons, and based on the substituents being different, each carbon is going to be different. So this one should be 6. So we would eliminate A and D. Does the meta isomer have a symmetry element we can use? It does not, so that one should be 6 as well. So that would eliminate C. And then the para substituted, it does have one element of symmetry. So that mirror plane that's going to bisect both substituents, split the ring in half. So that would be 4, and we end up with B. So B is the correct response. So I think the next couple questions deal with sort of proton analysis of that. And it says chloroanisole. So anisole is methoxybenzene. And so that would be the ortho isomer. The meta and then the para. And the question says there's 5 unique signals in the proton. And then within the parentheses, those are the multiplicities. And those come from the neighboring rule, the n+1. So it says there's 5. Just based on that, can we eliminate one of these isomers? So we can eliminate the para. How many signals should the para have?
3.
So it should have 3 in the proton. How many signals should the ortho have? So 5. How many should the meta have? So 5. So there's where we have these 2 possible responses that they're the same. So they can't both be right. So that's where we go to this multiplicity argument. So there's 2 singlets, 2 doublets, and a triplet. So within that, those pieces of information, what isomer would be the correct response? What? Meta. So let me point out first, you see the OCH3 group? It's obviously common to both, right? That's going to be a singlet in both cases. So you can eliminate that. And then the stuff that you're left with, the singlet, doublet, triplet, that belongs to the ring. So you've narrowed things down a little bit. And then you have this other singlet, so that's the key. You need to find an isolated hydrogen that has no neighbors. And so the meta is the only one that has that. So that hydrogen is going to be the second singlet listed. So we said the methoxy was a singlet. The circled hydrogen is a singlet. What should that hydrogen be? So that's going to be a doublet. This one will be triplet. And then this one will be the remaining doublet. Let's just run through the ortho to see how that pattern will change. We already know that the methoxy is giving it the singlet. So now how is it different from the meta? So that one looks like the one from meta, so it has to be a doublet. That one sort of maps on to meta as well, so that's a triplet. Now this one's going to be different because it has a neighbor, so that's going to be a triplet. And then the one next to the chlorine is going to be a doublet. So the sort of take-home message is here that you had these two which could potentially be right, so you have to look at this other data to differentiate them. So for that, we would get meta. So a couple more exercises, and then we'll get into some synthesis, and then hopefully at that time we'll shine the light on what is the crux of this whole issue here. So how do we predict which isomer will be formed? You have to look at what substituent is already existing on the ring. So we know that electron donating groups are orthopara, electron withdrawing groups are meta. So donating groups always react faster than benzene. So they're going to predominate. And then we know that they're orthopara. So is everyone good with that? Jump the gun there. Any questions? I think it's raining. I hear some pitter patter out there. So here is a situation for you. You have a molecule with two benzene rings, and we want to brominate it with Br2 and iron tribromide. At what position, A, B, C, or D, is the bromine going to go? No. Is it what? No. D is the correct answer. So the way you want to think about this, you have two rings. Think about them separately. What you're looking at is the benzylic carbon of each ring. That carbon is electron withdrawing. This carbon is electron donating. So the ring with the electron donating group has to win. And because it's an electron donating group, it has to go orthopara. And so on here, even though C is ortho and D is para, when you have a choice, para is preferred over ortho due to steric hindrance. So really, the logic funnels you into the correct answer. Once you identify those benzylic carbons, what are their substituents? If one of them is electron donating, that ring is going to win, and it's going to go orthopara.
You said that the para is preferred over the ortho because of what?
so sterics. And essentially what that means, you can imagine bromine like a really big ball. If you're putting it on position D, it's furthest away from, that sort of methyl group at the 4 position. If you put it at position C, it's really big, and then it's got this methyl group next door. So what that's doing is it's going like that. The substituents are pushing themselves away from each other, and that's steric strain. So if you were to run this reaction, in reality, are you only going to get reactivity at position D? Probably not. You're going to get a mixture of a little bit from C, but the major is going to come from D. Question?
Yeah, why is ADG always over EWG?
So the question was, why does the electron donating always win? So remember in the middle was our benchmark of benzene. And so electron donating groups, because they're pushing density into the ring, and through the mechanism, the ring is supplying electrons. So if the ring has more electrons, it's going to react faster than the withdrawing groups that can't supply it. So sort of same system, you have 2 rings within 1 molecule. So this would be called phenyl benzoate. And now we want to do a nitration. So we want to stick an NO2 group on there somewhere. So we have A, B, C, or D. So the carbonyl in general, how would you classify that? So electron withdrawing group. And then an oxygen would be electron donating. And then we look at the choices, from that oxygen. So A is the one that would put it into the para. So it can't go to B because that's meta. And if the oxygen's electron donating, it's got to go 1, 2, or 1, 4. Yeah.
Is there any scenario where EWG will win out over EEG?
I can't write one down right now, but conceptually I would say only if there's something interfering with it from the electrophile getting there. Some sort of, if there's functional groups around it that are going to prevent the ring from attacking the electrophile at that specific position. Yep.
Is there always going to be one EWG and one EDG in these?
No. So there's situations where you can have 2 electron donating groups on the ring. And then really what you have to do is look at the respective contribution of each. For example, so this would be paramethylphenol. And so the OH is donating through resonance, the methyl group is donating through induction. They're both blocking the other para position. And so, relative to the methyl, that's its orthos. And not relative to the hydroxyl, that's its ortho positions. So then you could say, they're both ortho para, which one wins? This one will win because resonance is a stronger push than induction. So if you were to do a third reaction, it would stick it there predominantly because these electrons go down and end up right here. So sometimes you'll have that scenario where they're not pointing to the same atom, and then you have to look at which one's stronger. But other times you get the situation where they both direct to one position, and that will just increase the overall yield of that. Yeah. Say it again. Diphenyl ether. So now since they're sharing the central atom, and the rings themselves are equivalent at this point, it really wouldn't matter which ring gets it. But if you took the product of that, then it would matter. So for example, because this is electron donating, we'll just say it would go to that para position. And then if you were to take that and run another reaction, it would really depend on what's the nature of that substituent, whether it's going to happen on that ring or the other ring. So that's where you have to start comparing what the relative effects of each of, like the oxygen versus what A is. So this is where we'll get into putting this into practice. So we'll look at this synthesis. There'll be a sheet with a bunch of different aromatics listed. We'll look at their substitution patterns. And then the last couple of slides basically summarize the strategy for putting this all together. So the case study is we want to make metatoluidine. Again, there's a common name. We know what the meta means. That's the 1-3 relationship. Toluidine is a mixture of aniline and toluene, but that's the name of it. And we want to specifically make that from toluene. So this is the retrosynthesis. So starting from toluene, how can we make metatoluidine? We said that alkyl groups were electron donating through induction. So that means it's an ortho-para director. So what is the issue here? So no matter what reaction you take toluene, whatever reaction you run first, it's going to go ortho-para. So that's not good, right? Because it's not getting the substitution pattern we need. So I want to just highlight this hydrogen. In toluene, it's a hydrogen. In metatoluidine, it's a hydrogen. But we learned reactions where we can stick something on, and then we can remove it. So because that methyl group is ortho-para directing, we're going to take advantage of that. We're going to put something at the para position to block it. Then we're going to take advantage of that reactivity so that it directs it to a subsequent reaction right next to that blocking group. And then we're going to finish off the sequence by removing the blocking group and unmasking it to a hydrogen. So that's going to sequence, those individual reactions we learned. Now we have to arrange them in a specific order. So I think the first thing that we'll do is we're going to nitrate. Because we remember that once we get the nitro group on there, we can do a lot of things. We can adjust the oxidation state, then we can do diazotization, and all of those sort of reactions. And we'll just assume for the sake of argument, although this could be different if we actually did it in the lab, that this is going to give us predominantly the para isomer. So now we have this situation. We have two substituents on there between the nitro and the methyl. The nitro is going to affect the directing ability more than the methyl, but they both align. So we know that nitro is a meta-director, so it's going to push there. Because the methyl group, we already installed something para. It would also align with how the nitro group is going to direct. So if we run a third reaction, we're kind of screwed because we're not going to get to the right pattern we need. So we're going to reduce the nitro group to the amino group. And so we can use hydrogen, palladium on carbon, and methanol. So we have nitro, we're going to reduce it to the amino group. So the amino group will take predominance over directing. So now it's going to direct there. So if I make that like a stronger, longer arrow, so that's where it directs. The methyl group directs there with a tiny arrow because it's not as powerful. So we can use that substituent to get us into the right place on the ring. And ultimately, we have to have a nitrogen there. So now we're going to do a second nitration. So fortunately for us, the nitrogen atoms are at different oxidation states. So even though they're both N atoms, we can act upon them differently with these reactions we learned. So we can selectively take out the one we don't need at this point. So it's going to be, so that's the one we can take out. So that amino group we can form the diazonium salt. and then react it. That should be H3. We form the diazonium. We react it with the hypophosphorus acid. That takes the amine back to the hydrogen. And so it leaves that nitro group alone. And now we have the correct relative positions, that meta relationship. The last step is just doing the reduction of the nitro group to the amine. So just to change things up, we can use the tin dichloride and ethanol. And we end up with the meta relationship. So the strategy is, really identifying, first what the substituents are, how do they act on the ring, and then if you see something weird, like it's not a natural sort of relationship of how the substituents direct, then you're probably going to have to use one of these blocking groups and remove it at the end. So that's 5 steps. So this is what pharmaceutical chemists do when they're making new drugs. They go through these sequences. The question?
It says M2. What does that say?
This right here?
Yeah.
Metatoluidine? Yeah.
Why does the nitro group attract the new bonds to that site specifically?
So in this strategy, this nitro group, so keep in mind, when I use ortho, meta, or para, I'm going to talk about like how one substituent directs a new one. And so then you have to talk about them sort of separately. But since this nitro group is a meta director, so meta to that is this position over here. This other substituent is an ortho para. The para is already blocked, so its ortho aligns with how the meta group is going to direct. So those two arrows overlap. So the next reaction, if you were to take this on, it's going to go right there. So that's why we have to switch its directing group ability through the reduction. Now once it's an amine, through resonance, it's going to, that para position's blocked, so it's going to direct ortho here. This ortho directing is a lot stronger than that existing one from the methyl, just because it's resonance. So in a way, you've differentiated those. And so since that one wins, it ends up in the correct relationship you needed from the start. And then at this point after, this is the unmasking or deblocking, and then the oxidation state change. Questions? So we'll finish off the lecture with. We'll do a couple more, but the compounds you see here are the compounds that I learned 30 years ago. So I'm paying it forward through Dr. Wheeler, my organic chemistry professor. And the challenge was, here are the molecules. Some of them, again, the names are kind of easy to figure out. Again, para is 1,4, bromo is bromine, and then benzoic acid. So this is the 1,4 relationship. This is the meta relationship. So, like anisole, if you don't know what that is, you can look that up. There's aniline, benzonitrile. So those things you can look up, but really what you're concerned about is the substitution pattern. Again, to restate, when you see ortho, meta, or para, that means there's only 2 substituents. If you have more than 2, then you have to start specifying their positions, because these are defined as those 1, 2, 1, 3, or 1, 4 only. So we'll look at, I think we have time to do a couple here. So para-bromobenzoic acid. So there's our benzoic acid. Para tells us that the bromine is at the 4 position. The constraint here is you can start with benzene or toluene. Toluene has a methyl group already on the ring. And so when we look at what we have to make, the benzoic acid has that carbon. So this carbon, that's 1 carbon. So we might as well start with toluene, so we don't have to worry about getting a carbon onto the ring. So this is an ortho-para director. So that's, again, through induction. We'll assume that the first reaction takes place with the para isomer being major. So I think I forgot a bromine here. So since we're starting with toluene, we need to get a bromine on there. Let's do that first. Uh-oh. It's on your phone. Don't worry, no storms or acts of God are going to stop me from teaching this. You're probably safer in here than running back to your dorm, so. So we're gonna stick the bromine on there. And again, we're just assuming that para is going to be the major. Practically speaking, if you did this in the lab, you'd get some ortho isomer. Then you'd spend the next 3 weeks chromatographing it out and hating life. But theoretically speaking, now we're set up. We got the relationship we need. The difference now is that oxidation state of that carbon is 0. We have to get it to oxidation state 3. So we're going to do a benzylic oxidation with the sodium dichromate, and that will get us up to oxidation state 3. That's the benzoic acid.
Morning. Now.
What do you want us to do? Okay. What?
We have a tornado warning, so everyone in the hallway.
In the hall? All right. See you later. Okay, so in this next example, now we're going to look at the meta substitution pattern for the bromobenzoic acid. And just like as before, we'll want to start with toluene because we have that carbon atom already bonded to the ring. The difference now being we know that the methyl group is an ortho-para director. So we're going to have to do a little bit something different in this case. We know we can oxidize that benzylic carbon and change its oxidation state from 0 up to 3 to make the benzoic acid. So that's what we'll start with. So we're at 0 oxidation state. We want to oxidize that carbon to the benzoic acid. So now we've taken care of that functional group transformation. So we're at oxidation state 3, and now, because we changed the directing group ability, we're able to put the bromine where it needs to be. So bromine, iron tribromide, that will get us the meta substituted pattern. So that's the meta isomer. So as you're doing these problems, you're looking at number 1, what substituents are bonded to the ring. Number 2, what are their relationships? And number 3, you know what the substituents are, you know the reactions, how to get them onto the ring. But now how are you going to sequence these reactions properly so you end up with the desired substitution pattern? So one last example of this, 2-bromo 4-nitroaniline. So again, since there's more than 2 substituents, we have to number the substituents separately. We can no longer use ortho-meta-para. And we have this substitution pattern. If we look relatively speaking, we could say this is a 1, 2, 4 tri-substituted benzene. And we know how to get the substituents onto the ring. So the amino group, we do a nitration, then a reduction. Bromine, we do a bromination. Nitro group, we do a nitration. So those are the 3 reactions, but now how do we sequence them? What do we need to introduce first so that we can take advantage of the directing group abilities? Notice there's no carbons on this ring, so the best thing to start with would be benzene. We have 2 nitrogens on the ring. They're at different oxidation states. So that's, again, something we're going to have to account for. The best way to start this is let's do a nitration. So HNO3, H2SO4. So now we have this nitrobenzene. The issue with that substituent, it's a meta-director. And, you know, we could do a reaction with bromine to get, you know, the 1,3 relationship between that nitro and the bromine. But ultimately, we're still going to have to deal with the nitro group being a meta-director. So the best thing to do now would reduce that. So we could take iron metal, HCl, water. That will reduce the nitro to the aniline. So now we have an ortho-para director, and as we said, if the para isomer will dominate, the next thing we can do is just repeat that nitration to get a nitro group in. So we have para-nitroaniline. And so these directing groups, we'll just make a note. This is orthopara, this is meta, and then just draw these arrows. So for the amino group, the para position is blocked, so now it has to go ortho. It's going to direct there. The nitro group is a meta-director, so it's going to reinforce that directing group ability, and that's exactly what we want. So we can finish this synthesis off with bromine and iron tribromide. And we end up with that 1, 2, 4 substitution pattern that is desired. So the strategy to start on these, this is either di or multi substituted aromatics. Convert the compound name to the structure. That's going to give you the visual sort of representation of the pattern you're looking for. Classify the substituents as electron donating, which are orthopara, or electron withdrawing, which are meta-directors. Recall the reaction conditions for installing each substituent onto the ring. So those are the reactions. You know, make sure you define their relationships. And then the most crucial part here, the last thing, you know, determine the order. So you know the reactions, now you have to sequence them properly to get them into that relationship. So what are some tips for carrying out this exercise? Benzene is the benchmark in terms of relative reactivity. Electron donating groups react faster than benzene. Electron withdrawing groups react slower. The Friedel-Crafts alkylation reaction installs an electron donating group orthopara director. So that's getting your oxidation state 0 carbon onto the ring. You can oxidize that carbon, so 0 to 3, to the acid derivative, which is now an electron withdrawing group or a meta-director. The Friedel-Crafts acylation installs a ketone, which is an electron withdrawing group meta-director. You can do the Clemmensen reduction, so you're taking it 2 to 0 back to the alkyl group, which is electron donating or orthopara. Also keep in mind the Friedel-Crafts acylation is what you use to install a linear side chain. because the alkylation may undergo carbocation rearrangement. And that would lead to a branched side chain. Nitration installs an electron withdrawing group metadirector. The nitro reduction to the amine switches that directing group ability to orthopara. And really the overall thing, the amine group is a surrogate for a lot of other functional groups. So hydrogen, that was your deblocking to put the H back on with hypophosphorus acid. Oxygen if you want to make a phenol derivative. The cyano group, which is electron withdrawing. Remember that the cyano group is equivalent in terms of oxidation state to the benzoic acid. And then finally the halogens, specifically fluorine and iodine. So at this point, don't forget to do your Module 1 exam. You have 24 hours. It closes Thursday at 2:15.